Okay, welcome everyone. My name is Kevin Hohen, and today I'm going to present a very interesting topic about quantum circuit quantization. This is the part one in which the idea is to cover the theory behind this, a bit of that. Okay, let's see what we know until now. Okay, so until now we know everything or pretty much all the things related with quantum computing. That is very useful because some sort of algorithms are very important in today's devices and today's applications, such as Shor algorithm, H8 algorithm, Grover algorithm. We can solve also optimization problems. We can use BQE or QA. Okay, with that in mind, we also, in order to do this, all the application and algorithms, we need quantum architectures, such as until what we have until now, there are like trapped ions, photons, neutral atoms, and superconducting circuits. And the idea today is to focus into the superconducting circuits. This is more related with the physical part or the physics. That is, that is in like it seems like this image. Okay, so why this is important? Okay, well, we until now we have that we can do all these quantum things related, but with all these like refrigerator, these all these electronics and you know everything else. But the idea today is to focus just into the chip design, such as like the teeny part and the most important part into the quantum computer. Okay, but before to begin with all that kind of things, we need to talk about the classical circuits. Why classical circuit? Because the idea is to do all these things related because we also use classical circuits into our devices. So let's begin with the inductor and the capacitor that are pretty common in the classical physics and classical electronics. Let's try to begin with the main equations of the inductor and the capacitor that are shown here. Okay, if we are trying to calculate the energy of such a devices, we have the equation that we have here that are like the kinetic energy and the potential energy. If we sum these two devices, like the inductor and the capacitor, we have like the LC oscillator. Okay, and why the LC oscillator? No, so the idea is to explain this. Let's try to calculate the energy in which are like the sum of the kinetic energy and the potential energy from the two devices. So in this case, we have the energy from the inductor plus the energy from the capacitor. That is this particular Hamiltonian. Okay, and this Hamiltonian is very similar to this Hamiltonian, and the solution of this Hamiltonian is a common oscillator, a quantum oscillator. Okay, with a frequency, of course, with a frequency in 1 over square root of LC. That is pretty very well known in all this kind of electronic and circuitry theory. Okay, so how can I promote this to quantum? But before to that, I need to take into account some particular things in which we need to mitigate thermal fluctuations and also have low or no resistance in our circuit and try as much as we can mitigate the coherent sources. If we have all of these complete, so we are checked and we can promote this to quantum. We need, in this case, to change our variable instead of voltage and current. We are working with flux and charge. And after that, we just change into the quantum variable that is more well known for phase and like the same chart, but in this case is referring to the Cooper phase. Okay, this right here equation are related with the voltage and the charge in a capacitor in terms of the flux. That, that will be very helpful in the next slide and in the next calculation. Okay, so let's try to rewrite the Hamiltonian, the same Hamiltonian that we have before with the oscillator Hamiltonian, the quantum oscillator Hamiltonian in terms of the LC oscillator with these two chain of variables. And with that, we have this Hamiltonian that is also very well known, but now is in terms of flux. That is better to work with that. Okay, so let's try to promote this to quantum. We just need to change the variable from this to the quantum Hamiltonian, and if you have doubts referring about the process, you can use these particular three equations. There are the charge flux relation, the reduced charge, and the phase flux relationship. With all of these, you can promote this into the quantum part. And finally, as you can see before here in the equation, we have the main variables in our circuit. That are not variables, are like constant values, that are the charging energy and the inductive energy. And the new frequency in our oscillator can be written as these two, well, taking into account these two other variables that are the EC and the EL. Okay, that's perfect. Let's now introduce a new device, that is the Josephson junction. And the Josephson junction is pretty simple in some sense. We are not going into deep into the theory behind this, but this is just a superconductor isolator superconductor device. This is pretty much, and there are the equations here that are the current, that is a critical current for the sign of, in this case, or phase, and the energy of the transaction, that are a particular like capacitance energy, and also the inductive energy, that is in this case is a nonlinear energy. Okay, so let's try to change our before or LC oscillator to another kind of oscillator that is compound and capacitor, and also this Josephson junction. But be careful, this Josephson junction is compound of a capacitance and also the Josephson junction. And with all of this, we have something that is very well known as a transmon. Okay, so now the total system is referring instead of the before, or taking into the account the system before, that are the LC oscillator, but we just change the inducting part, and the capacitance part is the sum of the two terms of the capacitance term. Okay, so what is the procedure to find any Hamiltonian given a circuit? Okay, so now we need to begin with find the differential equation, find the Lagrangian, after that find the Hamiltonian, and at the end quantize. So let's try to do it with our simple sample, the LC oscillator. Just to take into account, we are going to do the node theory from the circuit theory, in which all the current related with one node are equal to 0, the sum of all of that. Okay, so let's see that E1 and I2 are equal to 0. With this, we have that the current through the capacitor and through the oscillator can be written in terms of flux at the second equation here. With all of this equal to 0, we just need to say what is our Hamiltonian, and we just rewrite the equation to fix into the Lagrangian equation, which is in this case is this equation, the Lagrangian. In order to find the Hamiltonian, that can be easily calculated using the Lagrangian transformation that is written in this equation. After that, and after calculate all of these, we will come out with something like this, and we have, of course, our same Hamiltonian as before. Great. Now what? Now the idea is to don't do this video pretty long. The idea is to you try to come out with this Hamiltonian using the same procedure as before and have the same result as we had. Just remember, this box is composed of a capacitor and Josephson junction. So we have three branches. And just taking into account the current through the Josephson junction, and you will be okay. So, okay, thank you. Thank you so much, and I will see you in the next video.